Good morning, everyone. It's a pleasure, an honor to speak here at this important climate justice conference. I have a lot to tell you. I've received a long list of the issues I had to cover during my talk, so I will try to address all of them. I know I have too many slides. I know it. But you will all have them afterwards, and on some of them there's a lot of text. I don't want to read that. I don't want you to read that here, but sometimes it's to make sure that you are aware that these subjects are covered in the IPCC report. There is a reference to it at the bottom of the slide, and it would help you to dig in further if you wish. So my apologies for going sometimes fast on a few slides. I will go also slow on some other slides at some points. And inspired by Elise yesterday, I will start with a poem, maybe justifying such a long talk on the science of climate change at the beginning of the day. It's from a Senegalese poet. In the end, we conserve only what we love, he wrote. We will love only what we understand, and we will understand only what we are taught. So I'd like to use as much as possible in my talk and in my teaching this morning the content of the IPCC report. The IPCC stands for the Intergovernmental Panel on Climate Change, for which I have the honor to be one of the vice chairs. It's a panel of experts which has been established a little more than 25 years ago by two UN organizations, the World Meteorological Organization and the United Nations Environment Programme, not to do additional research on climate change, but to do something that's even more original in a sense, and that's to provide policymakers and all citizens of the world with the best assessed, digested, if you wish, information about the different dimensions of climate change, the science itself of the climate system, the science of impacts and adaptation and vulnerability, and the science, and when I say the science, it's in the broadest sense, the science of emission reductions, what we call mitigation. The three main questions that the IPCC tried to answer in its last report, the fifth report, published in 2013 and 2014, are the following. What is happening in the climate system? What are the risks? What can be done? And as I told you, I have too many slides. So in one slide, I will attempt to summarize the 5,000 pages of that report. So at least I have done that, and after, if I'm short of time at the end, you had the essential messages here. Human influence on the climate system is clear. This is a quotation from the last report. It doesn't contain any ambiguity. It's a clear message. Continued emissions of greenhouse gases will increase the likelihood of severe, pervasive, and sometimes irreversible impacts for people and ecosystems, and it's a general rule, unfortunately, as we heard yesterday, and this is also very well reflected in the IPCC report, that the poor are most affected and first affected in many of those impacts, and that's both in developing countries and in richer countries. While climate change is a threat to sustainable development, there are many opportunities to integrate mitigation, adaptation, and also, and that's very important, the pursuit of other societal objectives, such as increased air quality or water quality, and improved energy and water access to clean energy, eradication of poverty. There are ways to integrate the fight against climate change, or to adapt to climate change, and the pursuit of some of those other goals. That's very important. In summary, humanity has the means to to limit climate change and build a more sustainable and resilient future. One thing I forgot to mention is that I changed the title of my speech. If you read the title of my speech, you read that I spoke about the hidden message of the IPCC report, and remember that, because I will reveal the hidden message only at the very end of my talk. Now, we're talking about climate change. Maybe first we need to make sure that climate is indeed changing. You know, there are people who are spending a lot of energy and sometimes money to sow doubt about this issue, and they show you this kind of curve. You know, the temperature, the global temperature for the last 15 years. And, well, it's hard to get a strong impression looking at that figure that climate is warming, isn't it? Well, actually, you could have done that many times over the last 100 years by cherry-picking a starting date and an end date. And you could have argued that many times over the last century, the temperature has been cooling, has been decreasing. Really, this is lying with statistics. This is cherry-picking. You really need to look at the trends. You need to look at the whole series. And remember also that climate is not defined over 15-year periods, but at least over 30-year periods. Actually, and this is from the last IPCC report, if you compute decadal averages, you see that the last 3 decades have been successively warmer than each preceding decades, and even that the last 30-year periods, as in the northern hemisphere at least, for which there are data, probably be the warmest of the last 1,400 years, the warmest of the last 1,400 years. But there are many other indicators that climate is indeed changing. Look at this glacier in Alaska, as it was in 1961. Look well where the ice is. This is where it was 10 years ago. Disappeared. This is the behavior of most glaciers in the world today. Melting glaciers contribute an additional amount of water to the oceans, and this is one of the factors leading to an increase in sea level at the average scale. Average sea level has increased by approximately 20 centimeters over the last 100 years, as you can see here. And this is to a large extent due to the melting of glaciers. This is also due to the expansion of water as it is heated, and it is starting also to be because the big ice sheets, Greenland and Antarctica, unfortunately have started to melt as well. There are other changes in the atmosphere, in the climate system happening. For example, the increase in the CO2 concentration measured here in Hawaii on top of a dead volcano for the past 50 years or so. And as you can see, we have reached now approximately 400 parts per million. So we are talking here about the concentration in the atmosphere, the percentage, but the CO2 percentage in the atmosphere is very small, so it's measured in parts per million, ppm, and we are now close to 400. But this is very new in the recent history of the planet, because as you can see here, for the last 800,000 years, I repeat, for the last 800,000 years, the concentration has only changed between approximately 180 and 280 ppms. Remember, we are now at 400, so we have totally left the natural range of variations observed and measured in ice cores in Antarctica in particular over the last almost 1 million years. Why is this important? Why is this small quantity of a gas in the atmosphere so important? Well, because it is changing the energy balance in the atmosphere. If we didn't have the so-called greenhouse effect, we would have a balance between the energy coming from the sun, shown in yellow here, and the infrared radiation, the heat that is emitted by the surface of the planet in response to the heating by the sun. And the balance between those two kinds of radiation, one visible, the other one invisible, would lead to a temperature which on the average would be minus 18 degrees C. And life on this planet probably would not have evolved the way it has, and probably we wouldn't be here if we didn't have gases first studied in depth by an Irish physicist. And since we are in Ireland, I'd like to pay a tribute to him, and that is John Tyndall, who spent dozens of hours, even weeks, in his lab with his instruments, measuring in the middle of the 19th century the absorption capacity of different gases in the atmosphere. And he concluded that water vapor, CO2, he didn't measure methane at the time, but methane came later, had the property of trapping that infrared radiation and trapping the heat close to the surface. And instead of having that minus 18 C that we would have without those greenhouse gases, we have plus 15 approximately, plus 33 degrees. So the greenhouse effect is very useful. The problem is not the greenhouse effect, it's the excess of greenhouse effect, because if the CO2 concentration continues to increase, and if the concentration of other greenhouse gases, such as methane, which is also a greenhouse gas, trapping heat close to the surface, well, the temperature is going to increase. You can see here, and this is the kind of diagram to study at home if you are interested, you can see the relative importance of the different gases. This is for CO2 on a scale where the more to the right you are, the more important the warming effect is. This is the effect of methane, so it's far from insignificant. You have other gases as well. You have some factors, some pollution, air pollution factors, which also have a cooling effect. And this is the total. This is the total. And you see it's increasing from what it was in 1950. And you also can see that it is much, much larger than the effect over the same time period, which is the last 250 years, basically. It's much larger than over the same time period, the effect of solar irradiance, which is shown here. It's hard to distinguish from zero. So changes in solar activity have an effect on climate, but it's very small compared to the effect of greenhouse gases and the increase in greenhouse gas concentration due to human activities over the last 150 years or so. I've been asked to say a few words about methane in particular. So the concentration of methane has increased actually much more than the concentration of CO2. Its concentration has been multiplied by a factor of 2 since pre-industrial times. And this is mostly due to the massive increase in the number of ruminants, the emissions from fossil fuel extraction as well, because you should know that natural gas is mostly constituted of methane, which is a powerful greenhouse gas. 1 kilogram of methane is equivalent to 25 kilograms of CO2 if you look at the effect over a century time period. And there are also emissions of methane from landfills and organic waste. So it's important to understand and to try to quantify the effect of different factors, as you have understood, because the climate system is influenced by solar radiation and the changes in solar activity, which I just mentioned, but it's also influenced by in a major way by greenhouse gases. And I'd like to show here the results of an old climate simulation made in my institute more than 15 years ago, showing the separate effects over the last 150 years of greenhouse gases. That's the red curve in terms of warming, almost a degree, if only that factor was active. Of the small changes in solar activity, and you see it has a warming effect, it has had a warming effect, but much smaller than the greenhouse gases, and also sometimes it's an increase, sometimes it's a decrease. You have the green curve showing the effect of volcanoes, because when there's a big volcanic eruption, there's a cooling effect because of all the dust causing some shadow effects and preventing some of the solar heat to reach the surface. And then the blue curve there, the blue curve there is coming from the classic air pollution. And it also has a shadowing effect, a cooling effect. When you combine all those factors, actually, that relatively old model now, 15-year-old, was quite able to reproduce the black curve, which is the observed temperature. So the models are very important tools in the study of the climate system. And these tools are used to, today to quantify the solidity of the link between human activities and climate change. Because if there isn't a solid link, and if it was only human factors, well, it would be harder at least to discuss climate justice and the contribution of humans to the solution to the problems. So I'd like to show you again this observed temperature curve and the result of two types of simulations made with modern models. But it's in a very similar way to what I've just shown you for the different factors. The blue curve is obtained by forcing the model, by feeding the climate models only with natural factors. Natural factors being mostly the small changes in solar activity and the volcanic eruptions. And the red curve is obtained by feeding the models with all factors, not only the natural factors, but also the human factors, the greenhouse gases, and the classic air pollution. And as you can see, at the time of the assessment report number 1, AR1, in IPCC, that was published in 1990, well, there was a difference between the blue curve and the red curve, and the red curve is closer to the observed temperature, but the thick curves are the averages, and some of the simulations were not, there was a range around those averages. And so the IPCC scientists were very cautious. They didn't accept this as sufficient to conclude in 1990 that human activity was really needed to explain the warming. So it said unequivocal detection is not likely for a decade. Actually, a decade was not needed because in 95, at the time of the AR2, the assessment report number 2, it said the balance of evidence suggests a discernible influence of human activities over the last 50 years. Then, as time went by, as you can see, the divergence between the two types of simulations increased. It became clearer and clearer that without the human factors, there was no way to reproduce the observed temperature evolution. And so in 2001, it said most of the warming of the past 50 years is likely means 2 changes out of 3, due to human activities, etc., etc. Sorry. And to the last report said it's extremely likely, a probability of 95%, that human influence has been the dominant cause. So there is a link between the increase in the concentration of greenhouse gases in the atmosphere and the warming. But we have to understand where that increase in the concentration of CO2, in particular, CO2 is the main human greenhouse gas. It's about causing 80% of the increase in the heat trapping around the planet. So we have to understand a little better the connection between emissions of CO2 and the increase of the CO2 concentration in the atmosphere. And this slide is a slide I will spend a little more time because I think it's very important and very policy relevant, actually. First, in this unperturbed carbon cycle, you have two big loops. Exchanges between soils and vegetation on the left loop and the atmosphere, and the numbers there are labeled in gigatons of carbon, billion tons of carbon per year. Emission, a little less than 120. Absorption, 120 gigatons per year. The same for the oceans, a big loop there, emissions in the warmer part of the oceans of a little more than 70 billion tons per year, absorption of 70 billion tons per year in the colder part of the ocean, because cold water absorbs CO2 better than warm water. Now, we have perturbed these big loops, which were perfectly in balance, because if you add up the numbers, you had 190 going up, 190 going down. So as long as those numbers were equal, even if the numbers are high, the CO2 amount in the atmosphere remained perfectly stable. But we have affected this delicate balance which had been stable for the last 10,000 years, in this way. And these numbers are for the last decade of the 20th century, but we're just explaining the process, so unfortunately the numbers have increased, but to explain the process we can do this with these numbers. So emissions were of the order of 8 billion tons at the time per year, 8 billion tons of carbon per year. And if you translate the increase in the concentration that was observed into an absolute amount, a quantity of additional carbon, additional CO2 in the atmosphere, you came up with the conclusion that what was added every year was 3.2 billion tons of carbon in the atmosphere. So there's a mystery there at first sight. We were emitting 8 billion tons, mostly through the burning of fossil fuel, coal, oil, and gas, to a lesser extent also through deforestation. And a little less than 1/2 of that was found in the atmosphere as a remaining quantity. Well, the other half, I'm rounding numbers, actually was absorbed by vegetation, by increased absorption by vegetation and soils, and also in part by the oceans. So CO2 accumulates in the atmosphere because we are emitting approximately 2 times more than what natural systems can absorb. So without any climate models, a first approach in terms of numbers of the reductions in emissions that would be needed just to stabilize the problem, stabilize the thickness of the CO2 layer around the atmosphere, is a division by 2. But that's only a very rough calculation, but it helps to understand the order of magnitude of what we're talking about. And this, by the way, doesn't involve any complicated climate model. This is just arithmetics. Since natural systems absorb half of what we emit, well, we have to emit 1/2 of what we emit now so that there is a balance. Well, that's a simplified calculation, of course, but it helps to understand the order of magnitude of what we are talking about. But it's more difficult than that for many reasons. One reason, for example, is that vegetation is absorbing part of what we are emitting, but we are also deforesting. So, of course, we are cutting literally the branch on which we are seated, because we are destroying some of the absorptive capacity that is helping us. And also, as climate is warming, and as I told you, water absorbs CO2 better when it's cold, well, there will be less and less absorption in the ocean in the long term. So if there's less absorption, it means that the proportion, the quantity that will remain in the atmosphere will become progressively larger. For all those reasons, dividing emissions by 2 is actually not enough to really stabilize the temperature. The understanding of this carbon cycle, the main elements of this carbon cycle, is very important because it's also related to climate justice, actually. Because it means that emissions, which mostly occurred in developed countries up to now, in terms of global percentage, have accumulated in the atmosphere and remain, I mean, a part of those, remain in the atmosphere for a long time. Which means that it's not only today's emissions which matter, it's also past emissions, historical emissions. And of course, this is known in the climate negotiations, and it's a very important aspect to take into account. And it also is related to something I'll discuss a little later, the fact that the warming is very much a function of the accumulated emissions of carbon, which led to the notion of carbon space and narrowing carbon space as emissions are continuing. Where are those global CO2 emissions coming from in terms of activity? Well, mostly as far as the CO2 is concerned, from fossil fuel burning, and to a lesser extent, as I said, from deforestation. In terms of sector, and sorry, the black is not very readable there, my apologies, 35% from the energy sector, that's the biggest circle there, 24% from agriculture, forest, and other land users, so a significant amount. And we're talking here not on CO2, but overall greenhouse gas emissions, so including methane, N2O, CFCs, and other gases which have a greenhouse effect. 21% industry, 14% transport, and 6.4% the building sector. Now that we have understood that human activities really play a very important role in the observed warming, we can look at the future. And to look at the future, we have to use scenarios for the possible evolution of the concentration of CO2 and other gases. And this is for CO2, the 4 main scenarios considered. From the red scenario on the top, which is a business as usual scenario in our jargon, my apologies for the complexity of the name, it's called the RCP 8.5. And the bottom scenario at the other extreme, which is called the RCP 2.6, and which, as you can see, stabilizes essentially over the next 300 centuries the concentration more or less at the present level or slightly below. This is for CO2. You have the same here for methane. You can look at that later. And this is what happens when you feed those numbers, those scenarios, to climate models. And I only show you the 2 extremes, the top scenario, which is essentially a business as usual scenario, and the lowest scenario. And you can see that the lowest scenario provides an increase in temperature of approximately 1 degree Celsius above the present temperature. But we have had a warming of a little less than 1 degree already, so this is approximately a 2-degree warming, while the business as usual scenario, the red scenario, leads to an increase in temperature of the order of 4 degrees above the present temperature, and that means 5 degrees above pre-industrial. This is a bit abstract because these are average numbers. Let's look at what it means, for example, for India, for the top scenario in the worst case. This is on top of the high temperature India has, and you may have heard a few weeks ago the news about the death of a few thousand people because of heat waves just before the monsoon arrived in India. So if you add up several degrees, 5, 7, up to 5 or 7 degrees in India by the end of the century, you can imagine the human consequences in that region. It would also, sorry for the French, it would also be changes in the amount of precipitation, on the left for the lower scenario, on the right for the top scenario. Here, for example, in Northern Europe, in the top scenario, it would mean in most of Northern Europe, and Ireland is part of that, an increase in the average precipitation amount, while in North Africa and the southern part of Europe, it would mean a decrease with all the impacts you can imagine on agriculture. Sea level is due to continue to increase, of course, much more in the top scenario than in the bottom scenario, but sea level has a lot of inertia in the system, so it would still increase in the lower scenario by at least 30 centimeters by the end of the century. 1 meter by the end of the century. Again, to make this a little more concrete, this is what it means in the Nile Delta. For example, 10 million people were living 15 years ago, I don't know what the number is today, in the red zone shown here, which is the zone which is at less than 1 meter above the sea level. So you can imagine even half a meter would mean millions of people affected. It's also changes in the acidity of the oceans, which is shown here. The lower the number, the higher the acidity, again for the two scenarios, and it's much worse in the red scenario than in the blue scenario. Acidity has never changed much over the last 25 million years, and of course it would affect not human life directly, but marine life to have a much more acidic ocean, and you can see how large those changes that are projected are compared to the changes reconstructed for the last 25 million years. It would also mean changing climate changes in the extremes. For example, more extreme hot days, more intense precipitation. For Europe, it's including for Ireland, of course, it means very significant seasonal changes in heavy precipitation in winter in particular, what is shown here. The AGF means December, January, February. But also in many other areas. For example, in Kenya, a study that's quoted in the IPCC report estimated that under a range of scenarios by 2050, more than 300,000 people could be flooded per year under a high emission scenario. So impacts are really underway in a very wide manner, from the tropicals to the pole, on all continents and the ocean, affecting rich and poor. But as I said, the poor are more vulnerable everywhere. And this is illustrated on this picture showing something happening during the Katrina tropical storm 10 years ago, and reminding us that risk is not only a function of the geophysical hazards, the changes in physical parameter like sea level or intensity of wind during a tropical storm or whatever, but it's also a function of vulnerability and exposure, which are very much socioeconomic factors. And you can imagine that a black handicapped person in the middle of New Orleans is much more vulnerable than someone who has the means to escape the city with his SUV. So the potential impacts of climate change are very, very wide. Food and water shortages, increased poverty, increased displacement of people, coastal flooding are just a few of the examples. And in many, actually in all regions of the world, and I know this is too small, this is again something to look at home, impacts in many sectors, going from agriculture to health to forestry, have been attributed to climate change already. And this is with the small amount of climate change we have had up to now. In front of that, those emerging impacts, and this is just, unfortunately, only the beginning, adaptation is already occurring in many places in the world. For example, here in Bangladesh, and this is for Monsignor Gomez, where is he? I saw him this morning. Yes, there he is. There are adaptation efforts to create some refuge so that there is when there is a storm surge, people can escape the floods. But adaptation has, in this area and in all other sectors as well, its limits, as shown by this diagram showing the increasing risk level with climate change in two scenarios in particular. A world which warms by 2 degrees, where the warming is limited to 2 degrees by the end of the century, a world where it's limited to 4 degrees by the end of the century. And you see, and this is the conceptual diagram. I will now illustrate something real in a second. You see the risk level which increases when you go from the 2-degree world to the 4-degree world. You also see what is dashed here, the amount of risk that can be reduced through adaptation. So adaptation, in the example here, in the conceptual example here, has the potential to decrease the risk, which is most welcome. But as you can see here, the potential is not infinite, and it doesn't reduce the risk to zero. And also the potential might not be the same in a 2-degree world and in a 4-degree world. So let's be a little more specific now and look at Africa, where regional key risks have been assessed by IPCC in its latest reports for 3 important sectors: water, food security, and health. And look at food security in particular. We don't have the time to look at everything. But look at food security. There is a potential in a 2-degree world to decrease risk from a high value to a medium value, which is better than leave it at high, but it doesn't reduce the risk to zero, by the way. But look at the potential, which is extremely limited with adaptation to reduce the risk in a 4-degree world in the area of food security in Africa. So adaptation, yes, adaptation is very important, but it needs to be complemented, and this has been done for all regions of the world. This needs to be complemented by mitigation, because the risk of climate change increase with continued high emissions. And then there is that notion of cumulated emissions and leading to the carbon budget arising. Because if you map, and this is one of the new diagrams in the latest IPCC report, if you map the warming, which is the vertical axis, in function of the cumulative emissions, that means the total emissions, when you add year after year the emission to what has been emitted from the beginning of when you have data, actually here in the middle of the 19th century, you have something that's almost linear, as you can see. And when you do that kind of computation for the future, using the 4 scenarios, you see that whatever the scenarios, and of course there are some uncertainties around the results, you have a kind of linear relationship between the accumulated emissions and the warming. And this is very important, because it means that if you want to limit, for example, to 2 degrees the warming, you have, of course, with some uncertainty, you have an absolute maximal quantity of CO2 that can be emitted in the atmosphere. As you can see, if you take approximately the middle here of this curve for 2 degrees, it's a little less than 3,000 billion tons of CO2, okay? Which is shown another way on this carbon budget diagram. If you want to stay with a probability that's not so high after all, probability of a little more than two changes out of 3, if you want to stay under a 2-degree warming, well, the budget then, under that hypothesis, is a little less than 3,000 billion tons. The only problem is that we have emitted, and I say we, as I said before, it's mostly developed countries, more than 2/3 of those 1,900 billion tons of CO2 have been emitted by developed countries. So there's a remaining amount of the order of 1,000 gigatons, and this was until 2011, and we are emitting approximately 40 billion tons per year, so you see that there is some, and this is a euphemism, urgency. Another way to look at this is to see how the blue scenario I showed you earlier, the RCP 2.6, which is the only scenario leading to some stabilization close to the 2-degree warming, how it's compatible in terms of emissions of CO2 equivalents, so total greenhouse gases, with time over the coming 100 years. And as you can see, this scenario, this family of scenarios leading to a stabilization of the warming around 2 degrees actually crosses the zero line here well before the end of the century. So this means that well before the end of the century, it's a decarbonization of the world economy that's needed. But the observed trend is going another way because the emissions are increasing. These are the observed emissions at a world scale. The emissions are increasing. Now, there's a whole chapter I have in my presentation which I have not been asked to cover, and I know my time is up. But I have provided slides because I think it's important to have some information on those aspects because they are in the IPCC report also, and they will allow me also to say one word about the hidden message. So the IPCC says it is possible to mitigate. It is technically and economically feasible to keep the warming below 2 degrees. You will hear much more from other speakers about mitigation and about what is possible. But I will skip and go to the hidden message because you're probably curious what the hidden message is. The hidden message is that it's possible. On the other hand, you see that the trends are not at all going in that direction up to now. The emissions are still increasing, while if you want to go to zero, you have to peak and reduce. So what is lacking? Well, that's the hidden message of the IPCC report. What is lacking up to now, at least, is political will at the appropriate scale. Thank you very much for your attention.